Hello again and welcome to another GCSE Computer Science Theory lesson. This lesson is going to be on Unit 3, Audio. So to get started, you need to be aware that audio is made out of waves. Or it'd be more accurately to say that audio is made from pressure waves that your ear can then detect from vibrations on the very tiny bones that are inside your ear. But getting from all the physics and all that junk aside, just accept that audio is made from waves, which causes a slight issue when it comes to computer science. Audio is made from waves, computers work with binary, and representing something like a wave in binary form is pretty tricky to do. But stick with this video, I'm going to do my best to explain how that works. I'll start off with the theory, followed by a really terrible diagram in Paint. Then I'll go back to the theory again for a second time, and hopefully that might explain how it works a little bit better, or at least the level required for GCSE level. Okay, so here's the first part of the theory that you might need to regurgitate in the exam. Now, just an FYI for you, this explanation of how audio is recorded on a computer isn't 100% accurate. It is correct, it's just very watered down for the purposes of this GCSE. But anyway, I'll talk you through the steps. So let's imagine your homeboy Justin Bieber is recording his latest song on relationships, or how he's had a difficult and tragic life, or whatever garbage he sings about. Let's imagine he's in a recording studio. Well, he's got a microphone, which is a magical special piece of equipment that is capable of detecting changes in air pressure. So first of all, air pressure is picked up by your microphone. Second of all, the waves that have just been picked up by the microphone, the amplitude of those waves. And when I say amplitude is just a really posh word for height of those waves. So the height of those waves is measured at regular intervals. And when we say regular intervals, that is also known as the sample rate of a recording. So we take a regular reading of the height of those waves. And just for context for you, a low quality audio recording is sampled at 8,000 times per second. And 8,000 is a big number, so it gives you an idea of how much information goes into an audio file. And finally, these measurements are then stored in binary form. The next bit of theory that you might need to repeat in the exam is the definition of sample rate. So sample rate is defined as the frequency at which sound is recorded, or in other terms, the number of samples made per second. We use hertz to represent this unit. Hertz just means number of times per second. The other term you need to be aware of is sample resolution. So sample resolution is similar to amplitude. So amplitude is the height of your wave. Sampling resolution is the number of bits used to represent that height. So if your sample resolution, for example, was 255, so there were 255 different places you could measure your wave, well, in terms of bits, that would only be 8 bits, because you only need 8 bits to measure 255. Alright, so if this theory doesn't make sense at this stage, that's absolutely fine. I'm going to explain this in a bit more detail using Microsoft Paint. Then I'm going to go back over the theory again. So here's Microsoft Paint. And let's start off with step 1, which was air pressure is picked up by a microphone. So here is our little air pressure wave here. It's going to be picked up by a microphone. And then we're going to move on to step 2, which is where we measure the amplitude at regular intervals. So we paste this on here. Alrighty then, so we've got our little audio wave. We're now going to start sampling. So across is the sample rate, and going up is the sample resolution, or the amplitude. So amplitude being the height of the wave, but in computer science we're going to be referring to it as the bit depth or sample resolution. And just to clarify, this is over the space of 1 second, and I'm just going to do a little line to clarify that. That this up to here, the duration of that is just over 1 second. Alrighty then, so the sample rate in this example would be 10 because there are 10 points in which I'm going to be doing the sampling. So the sample rate is 10. And the amplitude, or the potential amplitude in this scenario is, well, we've got 1, 2, 3, 4, 5, 6. So we're going to have 6 different positions in which we can measure the amplitude, or that's going to be the accuracy of our measurements. In terms of bit depth, that's actually going to be 3. And I'm going to explain to you how I arrived at number 3. So first of all, we've got measurement 0. Let's call that 0. Then 1, then 2, then 3, 4, and then 5. Okay, so that's measurements 0 through to 5, 6 different intervals in which we can measure the amplitude of these waves. To measure the number 5 in binary only requires 3 bits. If we include 0, 0, 0, that gives us, we can allow for all 6 different measurements just by using 6 bits here. We could theoretically step it up to 8 bits, but in this scenario, I'm just sticking with 6 of them. Actually, screw it. Let's step it up to 8 bits. We might as well. We'll step it up to 8, especially as we're using 3 bits. So we'll call that 0, 1, 2, 3, 4, 5, 6, 7. So there we go. We can still represent 8 points of accuracy just by using 3 bits, because 7 in binary is 1, 1, 1. 3 bits. Okay, so now that we've established that our bit rate is 3 and our sample rate is 10, let's start by trying to accurately capture this wave. So do bear with me and be patient with my awful paint skills. I am using a mouse and keyboard, so this isn't going to be as fast as I'd like it to be with a touchscreen. Alright then, so here is sample number 1 here. Let's measure the wave as accurately as we can to one of these points. Now it looks closer to 6, so we'll measure the wave by here. So there's sample number 1. Sample number 2, we can get that pretty accurate. So there. Sample number 3, we can, well, that looks pretty much in the middle, but it looks closer to this one, so we hit it there. Sample number 4, this looks like the closest measurement we can get. The next one, probably by here. And the next measurement is by here. The next measurement is by here. Actually, I think the one above it is a bit closer. And the next one is definitely by here, followed by the next one, which is here. And then the final one looks like it's closest to this one. And there you have it. Those are all of our samples measured for the accuracy of the sample resolution that we're using. Now we do the process of just joining them up, and we don't have to join them up, but I'm joining them up just to show you what this original song will look like represented in a digital format. So there we go. I mean, my terrible paint skills aside, I hope you'll agree that it's quite difficult to accurately capture an analog wave in a digital form. As you can see in this example, this looks quite different to the original wavelength that we had. So you've got to ask yourself, what can we do as programmers, what can we do as audio technicians to improve the quality of our audio recordings? And there are 2 things that we can do. First of all, we can improve the sampling rate. So rather than taking 10 samples per second, why not take 20 samples per second? And for the bit depth, why don't we increase the bit depth? Rather than having 8 points of significance here, why not double it? And to double it, we only have to add 1 extra bit. So instead of using a sample resolution of 3, let's just double it and use a sample resolution of 4. And we're going to get considerably more accurate audio capturing. Okay, so going back to the theory, first of all, air pressure is picked up by the microphone. That's the blue wave in this diagram. Second of all, we take a regular amplitude, so we a regular sample, so 10 times per second. We've measured the height of the wave, so that's number 2, taking a regular measurement of the waves. And finally, step 3, we're going to store these values in binary. How do we do that? Well, I'm going to talk you through it. So this first point here is 6. And what is 6 in binary? Using 3 bits, because that's our sample resolution. So 6 in binary is 110. The next step is 5. So we're just going to write out 5 in binary, followed by 4, followed by 2, followed by 1, followed by 3, followed by 6, followed by 5, followed by 4, and then finally 2. And there you have it. This is how our audio would have been represented in binary format. And then the last bit of the theory, sample rate is the frequency at which sound is recorded. So just to clarify, this example, that's 10 times per second, so 10 Hertz. And sample resolution, the number of bits used to store each sample. So in this example, we have 8 different points of accuracy for measuring our amplitude. You only need 3 bits to store 8 different values. So in this case, the sample resolution is 3, not 8, not 7. The sampling rate is 3. And we have to be careful about that, because outside of the world of computer science, some people refer to the sample rate as 7 or 8 in this example. But for GCSE computer science, we refer to the sampling rate as 3, because that's the number of binary digits required. Okay, so that's all of the theory that you need to remember completely finished. The other type of question they could ask you about to do with this topic is a maths question. So they'll give you a context of an audio file. So in this example, we have an audio file that has a sample rate of 1,000 times per second, a resolution of 1 byte, and the track is 2 minutes long. What is the total file size in kilobytes? Okay, so approach this question. To get the file size, we just multiply everything we've been given together. So that's just times 1,000, times it by 1, times it by 2. Or at least that's a mistake that some students make. There is a little bit more to it than that. Notice that this says 1 byte. So it's not 1 byte, it's actually 8 bits. So 1 byte is 8 bits, so we can say 1,000 times 8. And when we say 2 minutes long, well, just be aware that sampling takes place per second, not per minute. So this isn't going to be, our calculation isn't going to be for 2 minutes, this is going to be for 120 seconds. And so we would have to do this. Here's the thing. Some students might be looking at this thinking, do we really have to do that mental maths in the exam paper? And bearing in mind, in the exam, there are no calculators allowed. So doing this off the top of your head, so 1,000 times 8, 8,000, then 8,000 times 120, that might be pretty daunting for some students. Well, here is a shortcut to make life easier for you, and I'm going to talk you through it. Well, it wants our answer in kilobytes. Okay, so kilobytes, kilo means 1,000. So straight away, we can get rid of that 1,000. So we're just doing 1 times 8 times 120, which is slightly easier, but still not easy. Well, it says bytes here, bytes, not bits. What's the answer in bytes? So we don't need that 8. We just change that to a 1. So here's our answer. It's just 1 times 1 times 120. So the answer to this question is just 120 kilobytes. Easy peasy. We've just answered a maths question without using very much maths at all. Okay, so here's the final part of the video. This part is completely optional, so feel free to stop watching now and move on. But if you're interested, I'm going to show you where you can use things like sample resolution and sample rate in a practical scenario on your computer. So feel free to follow this tutorial along with an audio file that you would like to try yourself. Okay, so here is an audio file that I have on my desktop, and here is some software called Audacity, which you can get free of charge just by typing it into Google. And I'm going to open the audio file with Audacity. Alright, so here's the audio file loaded in software, and I'm just going to play a sample of it for you. Okay, there you go. And I'm going to lower the sample rate and the sample resolution and see how that affects the audio quality. So here is the sample rate. I'm going to knock that down from 48,000 down to a mere 8,000. And I'm also going to save this project using an 8-bit sample resolution. Now usually these have a 24-bit or a 32-bit sample resolution. I'm going to knock it down to an 8-bit sample resolution. And I'm going to save this file and just compare how the audio sounds. Okay, so here's the high quality file and here's the low quality file. So here's the high quality one. And here is the low quality file. So there is a very noticeable difference in quality there. But next, let's take a look at the file size difference. And there is a pretty noticeable difference in file size. So the original was coming up to 64 megabytes, whereas the file with some of the quality removed is only about 2.6 megabytes. So there's a pretty massive difference there in audio quality.